Hello everyone and welcome to another Stat 437 lecture video. In today's video we are going to be talking about some of the theory behind the continuous time likelihood analysis that we introduced in the last video. So the basic idea of what we want to accomplish today is to take a look at the continuous time setting and see how our likelihood analysis sort of stems from there. So we're going to take a look at in detail, given a set of data that are subject to random censoring, how do we get out that likelihood expression that we saw? And we're going to be doing this in a fair amount of mathematical detail. And then I'll also try and show how do those assumptions that we were talking about, the independent and the non-informative censoring, how do those go about simplifying the process to something that we can actually work with a little bit more nicely. And also, we'll take a look at a specific example of how that likelihood analysis can actually help us. Okay, so with that, I will open up my whiteboard over here and we can get started. So the first thing that I want to do is define the likelihood contribution for an individual under random censoring. Okay, and so what do we mean by this exactly? Well, remember that for each individual, we're hypothesizing that there is some TI, which is the event time, and also there is some CI, which is a censoring time. And we've talked about different mechanisms for censoring. Sometimes those are going to be random, sometimes those are going to be deterministic. But what we want to do right now is work from the very general case of this just being a random distribution itself. Okay, and so in the last lecture, we introduced some notation about this, where we were going to use f of t, and we index that with theta, and say s of t, indexed also with theta, and that's going to be the density and the survivor function for our event time process. But then we also talked about how we can use, say, lowercase g, and we can use a phi here instead, and then we can use this sort of fancy g and with a phi as well, and these are going to be the density and survivor function for the censoring time process, right? And so what we're doing is we're thinking about this as there's two different events that we potentially could care about. There's the actual event, and then there's censoring as an event. And so we can think about jointly modeling the survival function of this in order to account for that random censoring that could go on, right? And we had talked about the observation is going to be, we had written it as this t tilde, right? And so that's going to be the minimum of, say, Ti and Ci for each individual, okay? And we also discussed delta I, which is the event indicator. So that's the indicator that Ti less than Ci. Okay, and so delta I is 1 if the event is observed, delta I is 0 if censoring is observed. Okay, and then the basic question that we want to ask ourselves is what is the likelihood for our theta and phi parameters? All right, and so we can start this by just thinking about what is our likelihood contribution for a specific individual. And there's sort of two cases for this, right? So let's just say that we're working with individual I. And the two cases that we care about are either the individual is censored or they're not. So I'll start with the not censored case. And another way of saying that they were not censored is that delta I equals 1, okay? So in general, when we want to write out our likelihood, what we're thinking about is what is the density or what's the probability of observing the data given our underlying model, right? And so what we have here is we're looking at an individual who we observed an event at some time t tilde, and we want to know what's the contribution of that to both the censoring time and to the event time, right? And the contribution is going to be sort of this probability that Ti is in some interval. And the way I'm going to write this, I'll sort of expand on specifically what this means, but I'm going to write it as that Ti is in this interval from T tilde plus D T tilde. Okay, and jointly with that, we also need to observe that Ci is greater than T tilde I. Okay, and so what does this notation that I'm writing right here mean? Well, this is the same thing as saying t tilde I less than ti, or I guess I can do less than or equal to uh, this plus some delta ti term, and then we take the limit as delta ti goes to 0. Okay, and so this is sort of the idea is we can't talk about the probability that ti equals small ti because it's a continuous time variable, and so instead we say what's the probability that it falls into this interval. It's just the density, right? This is exactly how we define the density, but I'm using this interval notation to sort of avoid having to write out these limits, right? And so an individual who is not censored has a contribution to the likelihood that is going to equal this probability expression here. Okay, and this probability expression is going to depend on the models that we select, but in general, it's going to be a function of theta and a function of phi, and it's going to depend on that joint distribution, and then we'll see how we can simplify down this joint distribution, right? But so that's the first case up here. In the second case, where we have delta I equals 0, well, what's the contribution there? And, I'd encourage you to actually think about this a little bit based on what we just said, but I'll write it out if it's not clear. The idea is that for an individual who we observe being censored, what we know is that ti has to be at least as large as our observed time. And in this case, ci now has to be in that interval that we were just talking about. Right? And so it's sort of the exact same process where we've flipped the roles of ti and ci. Sorry, that should be a d there. Okay, and so those are the two possible contributions to the likelihood, right? And we haven't said anything about what this joint probability actually looks like. But if we observe the event, then the likelihood contribution for the event process is that it occurs in sort of that interval. It's the density of that occurring. And if we don't observe it, then the censoring gets the same density. In both cases, if we observe the event, then the censoring has to be at least that large, and so we, use this condition of ci greater than. And if we observe them being censored, all we know about the event is that it would have happened after the current time, and so we sort of get that likelihood contribution there. Right, and so with these, we can actually write down our full likelihood. Okay, and so I'm going to sort of simplify this notation to prevent me from having to write out too much here. Right, I'm going to define this first one to simply be, let's say, p, we'll just call it p1, and it's going to be a function of theta and phi, right? And this one we'll define to be p2 as a function of theta and phi. And we're only doing this just because I'm about to write out the likelihood expression, and I don't want to have to actually type out that full expression. Of course, in the lecture notes that are posted about this lecture, I have the entire expression included there, right? So if we want the likelihood of theta and phi, we can write this as the product over all individuals, I equals 1 to n, of their individual likelihood contributions, right? And that's going to be this product from I equals 1 to n, and we'll get a contribution of p1i if delta I equals 1, so we can raise that to the power of delta I, times by p2i if delta I equals 0, so that's 1 minus delta I. Okay, and so that gives us this complete sort of likelihood expression here, and that's going to be in the general case, right? And so then if you wanted to work in this general case, what you would need to do is specify some sort of joint distribution for the event time and the censoring time, and if you specify some sort of joint distribution, you can derive what these two little expressions would have to be, plug them in, do maximum likelihood estimation from there, right? Now, in general, we're not going to actually want to jointly model those things. And so instead, what we would want to do is make a couple of simplifying assumptions, okay? And so what are the simplifying assumptions we make? Well, the assumptions are going to be that of independent and non-informative censoring. So let's start with independent censoring. Right, we've already seen these, but I want to, write these out sort of in full. The idea with independent censoring is that what we want to be able to say is that the censoring process is independent of the event process. Simply, we want Ti independent of Ci. And why do we care about this? Well, if we think about, say, that P1 expression that we were looking at, P1i, to be clear, well, we had this as Ti is in some interval here, up to D, and Ci greater than, right? But if these two expressions are independent, if Ti is independent of Ci, this becomes the product of these two, right? So it's the probability that Ti is in this interval plus Ti times by the probability that Ci is greater than T tilde I here. Now, the nice thing is that we actually can write these down in terms of more explicit functionals of these things. And so for this first component here, this is actually going to be the density of Ti evaluated at Ti here, parameterized with theta, and then we actually have to multiply it by this infinitesimal here, but that's going to go away when we ever look at anything, right? But it's just because converting from a density to a probability requires you to multiply sort of by that area there. But then the second term, sort of unambiguously, is the survivor function of Ci. And so if we get independence, we can actually break out these terms. And of course, we could do a similar thing with P2i, right? Where instead of it being the density of the event process, it's going to be the density of the censoring process, and then the survivor function otherwise. So this is going to end up simplifying down to the survivor function of the event process times by the density of the censoring process. That should be a phi instead of a theta, times by that infinitesimal there. Okay, and why do we like this? Well, now we can write out this likelihood here as the product from I equals 1 to n. We can take a look at sort of making the likelihood proportional to, we can end up dropping this Ti because we're just looking at the proportionality constant here. And so it's going to be the density here. And this first component is going to be P1i is always raised to the power of delta I, right? If we go back up here, P1i to the delta I, so we're going to have this component to the delta I times by, we have our survivor function there of the censoring process. That's also going to go to the power of delta I, and then we have P2i to the power of 1 minus delta I, so that's going to be the survivor function here, power of 1 minus delta I, times by g, and again, we can drop the infinitesimal because we're just fitting a likelihood, we only care about proportionality, and that's going to be a phi, 1 minus delta I. And so now what we have here, we zoom out a little bit to get the whole expression there, we have two terms which are related to the event process, and we have two terms which are related to the censoring process, right? But we've separated those out into these fundamental quantities. And so under the assumption of independent censoring, we don't have to jointly model them, we can model them independently, right? And so this would work as sort of the first simplification. Now, if what we're willing to do is also assume that phi and theta do not share any components, so you could write something like, if we assume that the intersection of phi and theta is the empty set, right? Then what we're saying is that the censoring process gives us no information about the event process and vice versa. And because we only care about inference about the event process, what we can actually say is that these terms that have to do with the censoring process, we can just drop, right? And so in that situation, we can say that the likelihood of theta is going to be proportional to this product of I equals 1 to n. We can include this first term here because that has to do with the event process. And we include the third term here because that also has to do with the event process. But we don't have to include the other terms because those are related to the censoring process, right? So they're not relevant to our discussion here, right? But the nice piece about doing this in this way is that we can actually get this simplified down a little bit further, right? And so What do I mean here? Well, if we break up the survivor function into, with the power, uh, write it out as the power here. So we can do this as I equals 1 to n. Survivor function to the power of 1. Write that out front because it's just a power of 1. Then we have our density here, up to the power of delta I. And then we would have the survivor function to the power of negative delta I, right? Well, because of this, what we can do is we could actually write this as the ratio. You can write this down in here to the delta I, and so we can put this whole expression here up to the power of delta I, remove it from over here. And the reason that we want to do this is because the ratio of the density to the survivor function, this right here, is exactly equal to our hazard function. And so what this means is that the likelihood, if we're making the assumption that censoring is independent and it's non-informative, we get the likelihood as the product I equals 1 to n. You take the survivor function times by the hazard function raised to the power of delta I. Right, so everyone gets a contribution of the survivor function. Those who have the event also get a contribution of the hazard function. Okay? And so that sort of becomes the way that we can simplify this expression of the likelihood. Now again, no, we haven't made any actual parametric assumptions, but if you were to make some assumption about the distribution here, well, this is going to give you enough that under those assumptions of independent, non-informative censoring, you can actually work with the likelihood expression. Right, so hopefully that makes some amount of sense. The next thing that I want to do here, and the last thing that we could do in this lecture, is actually consider this example of using the exponential distribution to walk through this process a little bit. Okay, so the exponential distribution, to remind you, we write, say, f of t. We would have this density as 1 over rho, where rho is our rate parameter, and then you'd have the exponential of negative t over rho. Okay, and so there's two different parameterizations of this. You might also see this as lambda times e to the negative lambda t, where then lambda equals 1 over rho, right? We're going to use this parameterization here. All right, we also know sort of from our past experience that the CDF is going to be 1 minus e to the negative t over rho. Right, and so what does this mean for us? Well, we can work out what the survivor function is then, right? Because the survivor function is 1 minus the CDF. And so 1 minus this expression here is just going to leave us with e to the negative t over rho. Okay, and so then the hazard function, well, how can we get the hazard function? There's a few different ways. The easiest way, I think, based on what we have here, the hazard function is the ratio of our density to our survivor function. Okay, and if we take that ratio, what you can see is that this exponential term is going to cancel out of both, right? And so we're just going to be left with 1 over rho. So this is our hazard, this is our survivor function, and hopefully the density and the CDF are quite familiar to you. Now, one thing that's interesting to note about this is that the hazard function for the exponential is constant. It doesn't depend on t, right? So it's what's called a constant hazard distribution, and you've already actually seen this in your past when you've seen the memorylessness property of the exponential, right? At any point, regardless of what has happened, there's sort of the same instantaneous probability of failure, right? It makes the exponential kind of an inflexible model because as a general rule, you would want to see that your hazard is increasing over time, normally. Sometimes you would have a non-monotone hazard where you have a high probability at the start, then it decreases before increasing again or something like that. But in general, a constant hazard is fairly restrictive, and so we won't actually use this a ton, but it's a useful example, and it does sort of come up from time to time. So given this, let's say that we wanted to have our likelihood of theta, right? And here we're just taking theta to be our rho parameter, but in other distributions you might require theta to be a two-dimensional vector or something, right? We said that the likelihood is going to be equal to the product, I equals 1 to n, And then we take the hazard function to the power of delta I. So the hazard is just 1 over theta to the power of delta I times by the survivor function, which is going to be e to the negative ti over theta, right? And so what we can do is then do our standard maximum likelihood estimation here, right? So we can write down our log likelihood. That's going to be sum I equals 1 to n, and we can take negative delta I log of theta minus 1 over theta times by ti, right? And if we then want to, say, differentiate this with respect to theta, that's going to tell us that L prime of theta is equal to, well, first, note that this log theta could come out front here, and so we would have negative log theta, the derivative of log theta is 1 over theta, so it's negative 1 over theta. Take the sum I equals 1 to n of delta I, and then here we're going to end up adding 1 over, the derivative of 1 over theta is 1 over theta squared. Negative, but we flipped the sign already. And then we have the summation I equals 1 to n t tilde I. Okay, and if we want to set this equal to 0 and solve, right, we can multiply through by theta squared, and we would find that our estimate for theta hat should then be equal to the ratio sum from I equals 1 to n of the times divided by the sum of I equals 1 to n of delta I. And so what is this sort of in words? Well, it's going to be the total time that we observed people at risk for divided by the number of events, right? And so if you wanted the MLE for the hazard here, well, the hazard is just going to be 1 over theta hat. And so you could flip that and say that the MLE of the hazard is given by the number of events that we observe in our data set divided by the total total amount of time that people were at risk. Okay? And so that's essentially all that I wanted to work through in the details of this lecture. So hopefully that all makes some amount of sense for you there. I hope that everything that we just discussed sort of made clear all of the conceptual topics we were discussing in the last lecture, and that you can sort of see where that likelihood is actually coming from. I think really the key point to take away there is that you start with this need to jointly model the censoring and the event processes. And then after you have this ability to jointly model them, we can make some simplifying assumptions, right? And so because specifying a joint distribution is sort of more difficult, we can assume independence if that's a reasonable assumption, and then we can divide that out into that first simplified likelihood. And then because we don't really care about that phi parameter, if we are willing to say that the phi parameter and the theta parameter don't go together, then we can make that further assumption of non-informative censoring, get down to that really nice easy expression to work with. And then as we saw with the exponential distribution, once you specify a distribution, we're just using standard maximum likelihood theory there, okay? And so hopefully that all made some sense. In the next lecture, we're going to look at some of the more theory around the location scale families that we were talking about and sort of see how those fit here. But remember that the exponential sort of can be transformed to the location scale, so it's all connected. Of course, all of the notes are posted on the course website, and if you have any questions at all with anything we've talked about, please let me know, and otherwise I will see you all in the next lecture video.